but you have a little added motivation that counts a little more than homework assignments. But it gives you an opportunity, forces you to look back at this old stuff, if nothing else, and you have all your tools available to you, fellow students included. So I want you to work with one another to complete this quiz. This would have been the quiz or quizzes that you would have gotten if I hadn't taken that Thanksgiving week off. But like homework assignments, I strongly encourage that you work together on it. I want hopefully to see a lot of perfects coming in. Don't just simply copy, but definitely work with one another. Make sure that you have the right answers on those quizzes. Get that back to me by Friday. Man. Did I miss anybody else? So I said Friday on this, but I thought we would at least take a look at the answers on this first page. So this is the absorption version and absorption and common identity versions of exclusive OR. So what did we say last time? How does this work? So if I have A, X, or A, B, how does that simplify?
A, X, or B, or
That's the common identity version, right? So if I have A, X, or A not B, that looks a lot like common identities where the A not cancels out, except for what else happens?
sign changes or no?
The operation, XOR changes to
Just the and, no, or just the or.
A or B. So this one's a loophole. You're told to pick either this or this. If you pick A, that's 1, therefore A not is false, and this is false no matter what, so you get to pick B for free. Because you did not pick A. This one's a trap. If you pick A and B, you've necessarily chosen both.
Right, so you just choose.
So you have to choose the A without the B. It doesn't quite look the same as the absorption, but I think of it as a stronger version of absorption. The only term you can have is this one. You explicitly have to say you can't take that one. You have to take the A without the B. I think we even went through a couple of these examples together. But we didn't get a chance to try a few of these. So you may not have tried this page, and that's fine. If not, jot down the answers so that when you sit down and try these problems, you know whether or not the answers are correct. Make sure you jot them down. Do that.
You missed one.
Yeah, I missed one. I updated all these worksheets, so I sat down and going through and updating the answer key as well. And I left this one blank on the older version as well. There's actually a reason for it. I may or may not take that one off in the future. We can talk about that one specifically. What's that? There's just so many possible answers. Yeah, that it's almost painful to list them all. So we'll talk about that one. That'll be one of the ones we work together. But I want to do a few that aren't quite so complicated. So we also talked about the De Morgan's law for exclusive OR. How do I apply De Morgan's law for exclusive OR? A or X or B not. If I want to break that not sign up, how do I do it with exclusive OR? Number that is on that rule sheet for exclusive OR. 9.
Yeah.
Okay, so what is A, X, or B not?
A not, E not. A not, X or B.
A not, X, or B. Or
A, X or B.
Right.
which is the same as A, X, or
A or
B
B.
not. Okay. So you get to choose to just leave a not sign over one of them. Why? Remember the explanation as to why that is? So exclusive OR in general is a count of whether or not you have an even or odd number of ones. Exclusive OR wants an odd number of ones to be true, either an even number of ones to be false. So a not sign, what it does is it takes whatever answer you have, a 0 or 1, and changes it. Right? Flips the answer. If I had a 1 here, the not would change it to a 0. If I had a 0, the not would change it to a 1. You get the same effect by just changing one of the values, because switching a 1, just a single 1 to a 0 or a single 0 to a 1 will change that balance of even or odd ones. So you only need to exchange one of the values. I think we even mentioned, I had it on here somewhere. There's a version of the number, Rule 16. It's related to this concept that A, X, or B is equal to A not X or B not. Along those same lines, if we think of exclusive OR as being an even versus odd number of ones, is that true?
Would just be right. No, then it'd just be effectively the same thing with that. Would just stay the same equation whether that's true or not, it would just be the same thing.
Well, exclusive OR breaks down into two types, right? Especially when there's just two. There's either same or opposite. If they're the same, XOR is true or false? False. Okay? So if I had a 1 XOR, well, this is getting into the truth table. I'm about to do a truth table explanation anyway, so let's write down the truth table. So A, B, 0, 0, 1, 1, 1, 1. A XOR B is 0, 1, 1, 0. What is A naught XOR B naught? Your 0, 0 in this case becomes 1 XOR 1, therefore false. Your 0, 1 becomes a 1 XOR 0, true. 1, 0 becomes 0, 1, true. And your 1, 1 becomes a 0. 0 XOR 0 is
0.
0. Okay? So those are the same. And this is an even or odd issue. An odd number of changes means you're finding the opposite of the exclusive OR. An even number of changes means you're finding the same value. Swapping an even number of 1s and 0s preserves the existing number of 1s or 0s that you had. Switching an odd number would change the balance of an even or odd number of numbers. So if we expand this to 3 variables, A XOR B XOR C not, how could I write the opposite of A XOR B XOR C?
It's true. As long as 2 of them are negatives or not, then can you do
2 of them would be the same
Right.
answer.
Yeah.
Right. So to maintain this as the inverse of A XOR B XOR C, we would want one change. C. So that would be the same. So imagine, under what circumstances is A XOR B XOR C true? Let's take one example. So ignore the not sign. When is A XOR B XOR C true?
If one of them is
If one of them,
or
no, because if one of them
No.
isn't 0, that means 2 of them
Right.
are 1. And in general, when you have more than 1, it's even or odd, right? So if you had, say, 1, 0, 0, that would be true.
Right.
XOR, XOR. That would be true. Therefore, the not of that would be false. What that not sign would then do, just over A, it would change my A, which was a 1, into a 0. Therefore, so you have 1 not XOR 0 XOR 0. Therefore, both of these would be false because you'd have 3 zeros. And that's what I mean by changing just one value, you upset the balance of even or odd, thus switching the answer, changing it from what was originally supposed to be a 1 into a 0. Without this not sign, we would have had a 1, but just switching 1, 1 would give it an answer of false. And I could do any one of those terms. So this would be the same as A XOR B not XOR C, which would be the same as A XOR B XOR C not. Because instead of flipping, say, the 1, the second term would look like this: 1 XOR 0 not XOR 0. By changing a 0 to a 1, I do the same thing. I have an even number of 1s, therefore the statement is false. So what would have been a true switches to a false. Same thing here. What would have been a true because of that one not sign changes to a false. But there's one other equivalent way of writing this. It's another equivalent way of writing A XOR B XOR C not.
Right.
Changing all of them.
Because of that.
Because it's an odd number, right? This is just an even or an odd. If you switch an odd number of the values, you're going to change the original answer. Just the same rule as here. So if we stick with this one example where I have 1, 0, 0, XOR, XOR, not, if I have an odd number of terms, switching an odd number of values is going to change the balance, even or odd, for the number of ones you have. This becomes 0 XOR 1 XOR 1, therefore false. And if I have an even number, this is expanding on this notion of De Morgan's law or exclusive OR. If I had A XOR B XOR C, I now can maintain the same answer if I invert an even number of operations. So this would be the same as, say, A naught XOR B naught XOR C. Changing an even number of those terms would keep the answer the same rather than change it to its opposite. If we look at the same example, 1, 0, 0. Now I don't have the not sign, so that's equal to 1 XOR 0 XOR 0 is true or false?
True.
1 or 0, 1. If I change two of the values, that would be 1 naught XOR 0 naught XOR 0. I'd still have an odd number of ones. Changing an even number would maintain that balance of even or odd versus changing an odd number. And that's what we get in the second page of this worksheet, where we have to apply V. De Morgan's law. So let's try 15. Before I can start simplifying, I don't have a rule for a collection of variables. So I want to break that exclusive OR up. What are my options for breaking up that exclusive, or excuse me, breaking up the not sign over those exclusive ORs?
Just change one.
Just change one. Instead of knotting all of them, I can just change one of them. Which one do you want to end up changing? Oftentimes it's arbitrary. The reason 18 is blank here is because you get different answers depending on which one you choose. So it doesn't matter. Let's choose the first one. A naught XOR B XOR C. So inverting the entire thing is the same as just inverting one of them. Changing just one term will change the balance of even or odd. XOR A, XOR B, XOR C. Now I can start putting relevant terms together. A naught XOR A.
It's just
So one.
Is 1. Yeah, they're always opposite. Those two are going to produce a 1. B, X, or B. If they're the same, they always produce a 0. That's going to be an X or 0. And then same thing with C, X, or C.
0.
0. Sorry, these are exclusive ORs. Therefore, my answer is
1.
1. And then just to prove the point, we could have invert an odd number. That's going to have the same effect as switching the answer. So just to prove this point, we could have said A naught X or B naught X or C naught. C naught, there we go. X or A, X or B, X or C. Now every pair of variable and its opposite is going to produce 1, X or B naught X or B, 1, C naught X or C,
XOR
1, and 1 XOR 1 XOR 1 is equal to
1.
1. Still at an odd number of ones, therefore true. So most of these examples, it doesn't matter which one you choose. If you're trying to invert a series of them, you just want to invert typically one of them. But if you invert an odd number, that would do the same trick. 16, for example, you only really have, because there's an even number of terms, you only really get to choose the one. You invert a single one of them. And most of these, you don't get that choice. Most of these, the not sign is only over 2 terms, in which case you can only choose to invert one of them. Shouldn't matter a great deal which one you choose. There are the exception here being 18. Every time I give this assignment, I weigh whether or not I should leave 18 on there. I think when I originally wrote this, I didn't intend for it to be this complicated. Well, let's take a look at why. A, B, X or B, C, X or A, C, X or A, B, C. In its current form, we can't simplify, so we want to apply exclusive OR's version of De Morgan's law, which would look like what?
Either one of them is knotted or all of them are knotted, I guess.
Yeah, so just 1 or 3, right? To invert a series of exclusive ORs, you have to change an odd number. So let's just pick A naught, X or B, X or C. B, X or B, C, X or A, C, XOR in a string of exclusive ORs is commutative and associative, so I don't need parentheses to be around the set of terms, even though the original not sign created that order of operations. So I can work now in any order I want. So it'd be one thing if you could just pick which one of these 3 you could simplify. The other issue that you run into with this example, why it creates so many different answers, is picking A naught isn't my only choice. I also would then get to choose which term, either AB or AC, should A naught get simplified with. And that would dictate which one I can simplify with B, which one I can simplify with C. So there's a lot of choices we can make from here. And it creates a large number of answers. Because now we're looking at that absorption and common identity version of exclusive ORs. For example, I could combine B with one of these two terms that contains a B. Doesn't matter which one. Let's choose that. How did those two terms combine? B or simplified? X or A, B.
A not B.
A not B. C could be combined with one of the terms that contains a C. Now, here's more choice. If I combine C with this, then I don't have the ability to use the common identity version of exclusive ORs. There's just so many choices here. So let's use this one. C combined with BC.
B not C.
Or B not C. Yeah, you have to take the C without the B. And then I can combine these two how would those two combine?
Might just be C.
That's this one here.
How do you get A not B again? So you just do from B,
A not B. These two.
yeah.
I'm applying
Trick question.
this rule here.
Okay.
That is, with exclusive OR, it's not really a choice between the two. I have to take this one. So that means I have to take the B without the A. And these two, same thing. It's not really a choice. This is a trap. I have to take the C without the B. Now the common identity version of exclusive OR looks a lot more like common identities with regular OR. The A naught
Knocks that out.
knocks out the A,
And you change the operation to regular
changes the operation to OR.
or regular.
So we're going to have an exclusive OR here, but then I'll have this A naught, regular OR, C.
Or C.
Now it's very subtle, but that is wrong. You know what I'm missing?
Oh,
Parentheses.
Parentheses. Yeah. They're regular OR and OR can't mix, right? They can't. They're not commutative and associative. I can't mix around the order. So I chose to put these two together first, and because there's a different order of operations between XOR and regular OR, I need those parentheses. So then we're out of our current rules. So we're stuck at this point. I can't simplify it anymore. But there are a bunch of choices we made along the way. we arbitrarily chose to put the not sign over A, for example. I chose to combine my A not with this term where I could have actually chosen to combine it with this term. I chose to combine my B with this where I could have actually combined it with the other term containing B. The C, I avoided the term with the A. I could have made another choice. So this is just one of, God, I think there's at least a dozen possible answers without any additional rules in exclusive OR form. So that's why I left this one blank. This is one of many, many answers. For example, show you another answer we could have gotten. Let's say we make the same choice of using A naught. Have A, B, so just copying out the second row here. XOR BC, XOR AC, XOR A naught, XOR B, XOR C. Let's combine the B's and the C with the two terms that contain A. B XOR AB,
A not B.
A not B. Good. Gotta take the term without A. XOR C,
A not C.
C. So then I have this term XOR BC that I didn't combine with anything, and I have this term A naught.
Take out one of the AB or the A not B or
Yeah.
A not C.
And here again, more choices that you could choose from, right? I could either choose to combine the A naught with this term or combine the A naught with this term. More possible answers.
So that one counts as a full answer though?
Yeah, given our current rules,
Yeah.
this is as far as we can take it. Okay? And you know, there might, just like ands and ors, I discover rules all the time. There might be rules that could simplify this and further. I don't know what they are. We're going to take a new approach to these problems, maybe starting today. We'll probably continue on Friday. But yeah, this is as far as we can go given our current set of rules. Here we have another choice to make, which is going to send us down a path of a whole bunch of different answers. But let's say we choose those two terms, A naught combined with the A naught B.
A not B not?
Would be A naught B naught. Have to take the A naught term without the B. XOR A naught C, XOR C, C. As far as I'm aware, well, I know we can't use exclusive OR in Karnoff maps. There may or may not be a Karnoff map version of exclusive OR where you make sure you write those variables in the correct order. That's as far as we can take it. So every choice you make in this problem sends you down a different path to a different answer. And this one choice gives us two possible answers because I also could have combined the A naught with the A naught C. Lots of different choices. So that's why that one's blank. On the last page, it's kind of a review, kind of continuing to explore the exclusive OR operation. It is true that AB or A naught C or BC is equal to AB or A naught C. Why is that? Are these two equal to one another?
Because of De Morgan or
Consensus.
Consensus rule. Yep, that's consensus rule. So I'm essentially asking, is the same rule true for exclusive OR? And as you can see with the truth tables, and make sure if you haven't done this, you confirm this yourself, that no, they are not the same. This one we talked about, but I never required that you memorize it. This one way you can justify this rule, you certainly could put it into truth table. But let me show you the algebraic justification of this rule. Let's see, AB or C or B C. These two terms have a common factor of C. Take that out. A naught or B naught. This is one of those partial factorizations that seemed like a dead end in the past. However, if I apply the opposite of De Morgan's law, I can fuse two naught signs together. If I put two naught signs together, what else do I need to do?
Change the operation.
Change the operation. So this would become C and
A not B not.
AB not or AB, in which case, how does that help? You got an AB, AB not,
You can cross it out.
There
by
you go.
common identities, you can cross it out. Therefore, AB or C. So these two would be an additional rule that potentially we could memorize and use to simplify algebraically. We saw this when I was explaining that just applying De Morgan's law isn't simplification. You certainly can apply De Morgan's law and get yourself into a bit of trouble. If you started here, applied De Morgan's law, now it appears like we're stuck. Maybe you could throw it to a Karnoff map and see that that could simplify further. You have a question?
Yeah, I just have a question on when you switch.
Oh, okay. So then, is the same thing true for exclusive OR? Plug in, if you haven't done so already, get some extra practice plugging those into using truth tables for exclusive OR, and you'll verify that no, in fact, those are not the same. Okay, your question?
Yeah, just on number 16 on the other side. I did the where you do you're supposed to like B naught. You can choose between B naught or C naught.
Yep.
So B naught or C and or A and or B and or C.
Mhm.
It comes out to 1 plus 0 plus A. And wouldn't the answer be A then?
Exclusive. Okay, so B naught was your choice. C XOR A XOR B XOR C. So you paired out C with C and got
0.
0.
B naught B.
B naught would be 1, and then A doesn't have a match. 0 XOR 1 is 1. XOR A is You're just forgetting this rule.
It's just the XOR.
Yeah, it's exclusive OR. One X or A is actually a not.
So it's exclusive OR only if you can't get them all into ones and zeros. It's exclusive OR pretty much. You know.
Well,
like,
it's exclusive OR
It's a
unless you
solution,
can
not
change it from exclusive OR,
Exactly.
right? So everything stays exclusive OR. The only rule we have right now for, I erased it, that will switch exclusive OR to regular OR is that common identity rule. That changes exclusive OR to regular OR. So yeah, everything in between each one of the remaining terms is exclusive OR unless you're able to change that.
Yeah.
Okay. So I'll give you a little extra time working with P17. Try those problems, copy down the answers, yes, but give them a try. 18, I probably should just remove that. That's a mess. I don't think I really intended to be that messy when I originally wrote it. All right, so I'm going back to this supplementary page of rules on exclusive OR. I don't want to see how far we've gotten. So let's go through these. 5 is true of true.
True.
6,
True. True.
7,
True.
8,
True.
9,
False.
10,
True.
11,
False.
12,
True.
13,
False.
false, 14,
True.
true. Let's see, we talked about, oh yeah, we've mentioned 15.
Yeah.
Is 15 true or false?
True.
False. Yeah, so what I'm implying there, that's the order. Left to right versus left to right doing the OR first versus going right to left doing the exclusive OR first. We've alluded to this a number of times. Order matters here, so 15 is false. 16, we may not have, I may not have told you to write it down on your sheet, true or false?
True.
True. Switching an even number of operations maintains the original expression as opposed to odd, switches it. So then we're down to 17 and 18. So we'll probably have just enough time to talk about 17 and 18, and then we're going to use those rules in application on the next worksheet. Which did I post? Did I post 18?
No.
I did? Okay. We'll get it up there just so you can start twiddling with it, but we'll talk more about that on Friday. Collect 18 Monday. Everything back today. We have time. We're in good shape with this class. Alright. So. This is number rule 17. True or false? A or B, and A, B, not. Without putting it into a truth table, anyone want to venture a guess if that is true or false, and maybe why? False. Say false. Okay. Or and exclusive OR are very close to one another. Right. Or and exclusive OR are very close to one another. Under what circumstances do they differ? Just think about these simple OR and exclusive OR operations and compare those. We have A or B versus A XOR B. 0, 0, 1, 0, 1, 0, 1. Regular OR is false, true, true, true. Pick one, the other, or both.
Right.
Exclusive OR is you can only pick one in the two variable case. So exclusive OR and regular OR, for the most part, most of this truth table, they're exactly the same. Everything above that green line OR is the same. in those three cases, your and A, B not here isn't really going to change anything. In all three of these cases, you have 1, 0. One or both of these are going to be equal to 0, in which case the not would change a 0 into a 1. So anding 1 in those three cases doesn't change my answer. The only time this changes an answer is here. When you have 1, 1, 1 and 1 is 1. This is not, so it's going to change my A or B 1 at 1, 1 into a 0. These two are the same thing. What you're saying is exclusive OR is the same as regular OR, and you have to, if you preclude the A and B case. Exclusive OR, regular OR are the same as long as you don't allow for A and B. So these are actually the same. In terms of logic gates, there's still only ands and or logic gates. This is the way you wire together an exclusive OR. So these are the same. Rule 17 is true. How about 18? A x or b is equal to a b naught or a naught b. True or false?
It's true. True, because you can just cross them out.
It's the same.
Well, it's the same thing, right? It's
Right.
either you get A without B
Right.
or you get B without A, right? It's just laying out those two choices. These two are the same. And if you believe me, this is true. We can use techniques that we've been practicing. A or B applied to Morgan's law. That would give me A naught or B naught. Distribute. A and A naught is 0, or A B naught, or A naught B, or 0. Therefore, that. What these last two rules do for us is give us a way to change exclusive OR, change from exclusive OR. The last worksheet we're going to work on has you practicing these techniques. I used to have students apply, I usually prefer this rule. I used to have students apply this rule and do this change all algebraically. But a student a couple semesters ago say, well, why don't we put it into a truth table and apply the techniques of changing truth table into a Karnoff, from a truth table through a Karnoff map to write it as or an exclusive OR, and that made life a lot easier. So that's the way we're going to do this. We'll talk more about that on Friday. Finish up 17, get that in on Friday. I'll post worksheet 18, and you can start looking at it. But we'll work a few of those examples together.
Thank you.
Thank you.
For number 10, I'm getting sick.